好，等一下我们也会邀请林师协助我们口译哦，谢谢。
我想在座医师应该都不需要口译，但是如果真的有困难，我们将可以帮忙。
Please, hello. Yes. See you.
That's good. Next question is, can you see my screen? That's the next question. Can you see my screen?
Hello. Hi, Dr. Max. We can see you now. You should start now.
Okay. Great. So I don't know if you see my screen. Good morning, everyone. Just try to make my screen share with you, and we can start. Okay. Can you see my screen now?
Yes.
Yeah. Good. So good afternoon, everyone. My name is Max Boyset. I'm the CEO of the company Swiss Advanced Vision, and I'm going to give you some inputs on the technology of Lucidis and instant focus as well. So maybe first of all, a couple of words about us. So Swiss Advanced Vision, we call SAV-IOL. We are in Switzerland. We are a Swiss manufacturer. And basically, we are a very tiny, small company with 20 people, and we are selling to more than 30 different countries over the world, including Taiwan for sure. So the particularity is that of our product is that each IOL has a patented technology inside called EDOF and called instant focus. And I know that the doctors just before me talked about it a little bit. I will try to complement what they said on the more on the technological side and explain you a little bit what EDOF is or can be and what's the technology that we are actually using. So in summary, talk a little bit about what is instant focus and what are the typical benefits directly from this technology, meaning having no rings, and therefore no halos and no glares, which is very important for the patient. And the results behind that, point 3 and point 4, is that we have a very high satisfaction level for our patients. And for sure we have a defocus curve, and I've seen that being presented already, which is very flat, and we're going to see that afterwards. First of all, I would say the technological specifications. So we are talking about an hydrophilic implant with 26% water content, CI26. The size, we have actually two. The optical size remains the same in both cases. It's a 6 millimeter diameter, and the optics can be 10.8 or 12.4. It's really a difference that is up to the surgeon to choose, and not to the patient for sure. But again, the optical remains the same, and you see on the screen here that the optical is made of two parts. The center part is called the aspheric surface, and that's a 1 millimeter disc. And the large one is the refractive surface, and this is for the far vision. We're going to see that. In the very center here, on this aspheric surface, this is the place where we're going to create this EDOF, and we're going to see how. The add value and the EDOF values are around 3, meaning that the add is really 3, meaning the reading distance is 33 centimeters, and the add value is around 3 as well, meaning you add 66 centimeters to the reading distance. So from the point you see to the end of the intermediate pin, it's more than 1 meter, which is totally clear and with no disruption in terms of vision for the patient, which is very important. And the injector size, our recommendation is really to be more or equal than 2.2 millimeters. Light distribution, you have seen that before. Just a comment on what you have seen. What is remarkable here is that under photopic vision, you see that the distribution of light is really equal. 1/3 for the distance vision, 1/3 for the near, 1/3 for the intermediate. And if you move to mesopic or scotopic vision, then for sure you've got a large predominance of the distance vision, and you see that the near and intermediate vision are at par, more or less. And that's very explainable with the fact that, again, on the very center of the lens, this is the place where we address the near and intermediate vision. And the more you open, the more you have a distance vision because you are attacking or you are addressing this monofocal EDOF type of lens. I'm going to come back quickly on that thing. If you see here, the type of lens, we are really talking about a pure monofocal. And at the very center, we have add this aspheric surface with 1 millimeter diameter. So of course, the more you open, the more you get close to a monofocal, meaning the more you get close to the 100% distance vision. In terms of defocus, this is as well very remarkable. This is visual acuity view, and if you see from 0 to -3, which is the range which is very interesting, this is really flat, and this is really above 0.8 or even 0.9, even 1. And no one is doing that. If you compare to others, which have been shown already. So this is the logmar view, this is the reverse, but we are talking about the same thing. And here you see the curve for Lucidis, and you compare to our competitors like Anoptics, Symphony, IENS, or even other monofocals. So it's really flat, and it's really close to 1.0. As a result of that, people can see very progressively there is no disruption of vision. And one of the big success of Lucidis is really linked to this Defocus curve that no one really had today in the competition. More technically now, how does that fly? What's the mechanism behind it? There are many ways to create EDOF. You can either create EDOF with diffraction. You can create EDOF with offset of spherical aberration. And one way of creating EDOF that we are using is to use what we call the PND beam, the pseudo non-diffractive beam. So, don't want to lose you, but just to give you a little bit of background with that. A PND beam is behaving between a laser, which is a pure non-diffractive beam, and a diffractive beam. So it's really what you see here in the middle. It's like a laser in terms of behavior in the middle, meaning it's parallel, and it's diverging from the two other sides. This is really what we are producing thanks to the very center of the lens. And if you look at the technology instant focus, this is what it is. It's a combination between the extended depth of focus that happens in the middle and what happens on the peripheral, meaning getting the far vision from the monofocal. And with this combination for Lucidis, we get the two benefits. The benefit from a monofocal with no rings and a strong far vision, and this very center that provides the near intermediate. So, just to go a little bit more on the technical side, just for information, we are using a couple of principles. The first one is really Basal beam. So what is a Basal beam? So in a nutshell, it's a wave which is behaving like a radio interference. And this wave is a non-diffractive wave described by a Basal function, which is a mathematical function with a Basal differential equation. This is what we are using, and you're going to see that afterwards. To create this Basal beam, you may want to use a lens. And there are a type of lens called axicons that are either convex or concave, that will create a type of basal beam or basal beam-like type of waves. You see here an example of axicon. If you would, the axicon will transform a laser that you can see on the input, laser-like beam, to a ring distribution beam, or ring shape distribution ring, like radio interference, as I mentioned before. And this is what we are looking for here. This is really how instant focus is working. In other words, we are moving a Gaussian beam to a non-diffractive Basal-like beam. And as a result of that, what is important in terms of technicality is that we are getting this kind of diamond shape that you can see here, which is created by the axicon. And this is the base for having this elongation of a beam that we call the EDOF, extended depth of focus. If you look at it, another view from this axicon, here we are creating this very small diamond. So this is pretty simple. This is the simplest we can get in terms of principle. But this is the start of the EDOF. Then if you have this, again, this was more like a laser beam that is in input. And as an output, you get this diamond. Then if you now put as an input a Gaussian beam, you get this diamond, which is very complex. And at the end, in terms of distribution, you get this EDOF, extended depth of focus, which is really looking like a diamond. Now if you combine this axicon on the right and this lens on the left, you can get with what we have in for instant focus, meaning having a constant resolution of light around the point of focus. In other words, here, this is what we get really in terms of mechanism. As an input, you have a beam, which can be either considered as a laser beam or a Gaussian beam. And you have at the surface of this aspheric element in the middle, you have those different slopes that are behaving like multiple axicons, or an infinite number of axicons. As a result of that, on the right, you see here around the retina that those interferences will sum up and will preserve the beams for the near and intermediate vision only. So in this yellow zone that we call here in the middle of the extended depth of focus, you're going to have a resolution and the light intensity that will be just constant. And that's going to be really the operating mechanism for our lens, and especially for Lucidis. So for sure, having that big difference between our product and the others are creating a lot of benefits for the patients. At the end of what we are looking for. So the first benefit is that having no rings means no diffraction, having no halos and layers. That's key. That's the number one benefit that immediately you get from the patient feedback. They are free of halos, free of layers. Another benefit is that the chromatic aberrations or the chromatic dispersions are far below what we can see. Again, still thanks to the absence of rings in our model. And that's a huge benefit. Another benefit as well, which is significant, we have seen that multiple times, that after surgery, the neuro adaptation time is very, very quick compared to other IOLs containing rings. So that's as well another benefit which is very important. Another view on that slide is interesting, comparing having or not having diffraction rings. Above you see that this is our case, we have no diffraction rings, so you see really a distinct single focus. And at the bottom you see the reverse, meaning the effect of having diffraction. And this is leading to another point, the degradation of energy. When you have diffraction rings, for sure you are losing energy. And we have made an evaluation that our Lucidis lens is having less than 7% energy waste, meaning we are preserving 92%. While in best case for the other IOLs with diffraction rings, we are talking about a 15 to 17% loss of light. So having this absence of diffraction ring allows us to focus really on what's important and not losing the energy of the input beam. So this is the summary of what we have in terms of technical specification. At the end, what is important for us is that we have now more than 3 years in terms of history with Lucidis, more than 10,000 cases over the world, and the feedback remains constant with almost 100% people being satisfied, which is very good. And what is really common is that there is no halos, no glares, and no loss of light. As a result of that, people can read starting 33 centimeters and very progressively since infinite, and they have not this drop of vision that you can see with other IOLs. That's about it for me. And I'm ready to take any questions if you have.
好的，现场有没有医师先进有要询问我们 Next 吗？有没有医师有问题的？有吗？有问题想询问的吗？哦，好，来，林医师。
Hello?
Dr. Max, can you hear me?
Yes. Yes, I can hear you.
Thank you very much for giving us so elegant, so complete lecture. So I have a question. I'm Dr. Lin from Taipei Veterans General Hospital. I would like to ask, for the current available Lucidis intraocular lens, about how much of the so-called extended focal length?
You mean in terms of add or EDOF, or EDOF value?
Yes, value or angle, whatever.
The angle, the kappa angle?
The
Value.
The
value.
If you look at first of all, the EDOF value is read +3, starting from the reading distance. And the kappa angle, or the angle of tilt, I didn't mention that, but what we observe is that you can tilt or decentrate even Lucidis. It's very tolerant, more tolerant compared to Symphony or other lenses. So we have seen cases where we know it has been decentrated or even tilted, and still you have a very good result. So it's much more tolerant. So in other words, one of the reasons we get a high level of satisfaction is that sometimes it's not easy to put it right away, and sometimes it's tilted up, and still we have good results.
Thank you very much. But I'm going to make myself more clear. I mean, about how many millimeters of the current available Lucidis are about the so-called extended focal length. And I mean, how big is the focal length? How many millimeters?
How many millimeters? The size of the implant, or the size of the optic?
The real value of the focal length.
I have a hard time hearing you, sorry. So I'm not sure to get your question. What?
Okay, I'll ask you later.
Millimeters of what?
Any comment from the audience? Any question?
请问还有医师还想要询问的吗？两位医师。
Thank you for your participation. So I think our seminar is wrapped up. So thank you for your participation. All right. Thank you. Bye bye.
好的，非常谢谢 ，Thank you。有没有确定医师都没有要提问的哈？好，那我们也谢谢我们的 Dr. Max，Thank you，拜拜，可以去补眠了。 也是询问现场我们现场所有的医师们，那有没有想要提问我们现场3位演讲的医师呢？